Well, good evening, everyone. My name is Mike Sullivan. I'm not the person in the box right there that you may be looking at. Welcome to this evening's Evening Skidaway program. I think you're really going to enjoy it. Our speaker, Dr. Chris Marsay, has an interesting mix of science and adventure for us tonight. We also do appreciate you bearing with us as we worked our way through some of the technical issues of trying to do this virtually during the pandemic, and I hopefully we've got most of the issues worked out. We're going to hold questions till the end of the program. To ask a question, you can use the YouTube chat box to type in your questions. We'll have someone monitoring that and relaying the questions on to Dr. Marsay. And Dr. Dan Onimus, who's monitoring that, is also going to provide, if you don't have a Google or a YouTube account, a little workaround on that, a little link in the chat room that can allow you to ask a question even if you don't have a YouTube or Google account. At this time, I'd like to introduce Dr. Chris Marsay. As it will be very obvious in a moment, Dr. Marsay, born and raised in the UK. He received his undergraduate degree in chemistry from the University of Sheffield, a master's and doctorate in oceanography from the University of Southampton. He considers himself and is a chemical oceanographer, and he's been at Skidaway Institute since 2015, working in Dr. Cliff Buck's lab. So without further ado, Dr. Marsay, take it away.
Okay, thanks, Mike. I hope everyone can hear me clearly. So this evening I'm going to be talking about my time in the Arctic last year as part of the MOSAIC project. So I'm going to start off by giving a very quick introduction to the MOSAIC project, and then I'm going to spend the first roughly half of my talk talking about the scientific motivation for the project and giving a more thorough overview of the project design. And then the second half of the talk, I'm going to be talking more about my own personal experience being involved with MOSAIC, including the training, the challenges that came up as a result of the COVID-19 pandemic, and just what it was like working in the Arctic. And then I'll finish off with one final slide that goes over what happened after I left the floe. So throughout this talk, I'm going to refer to the MOSAIC project. That's actually the shorter name. The full name of the project is the Multidisciplinary Drifting Observatory for the Study of Arctic Climate. And this is a very big and ambitious project. It involved a 1-year-long field operation in the Central Arctic Ocean. It was led by the Alfred Wegener Institute in Germany, but there were more than 80 institutions from 20 different countries taking part. It had a budget of in excess of $180 million. And over the course of the year, at least 440 people from at least 37 different nationalities worked in the Central Arctic for some part of the 12 months. So that's a lot of resources to be used in a particular project. So the obvious question is, what is the scientific motivation for that project? Well, this figure shows the change in global temperature over the last 50 years. And the greater that the change from yellow to orange to red represents a greater increase in temperature. So what this is showing, what I want to draw your attention to, is that for the Arctic, the whole region is red, which means that it has warmed to a greater extent than the rest of the planet over the last 50 years. And in fact, during that time, the Arctic has been warming at a rate approximately double the global average. This figure shows the seasonal change in Arctic sea ice extent. So at the bottom here, we have months going from January through to December. And the vertical axis shows the aerial extent of sea ice coverage in millions of square kilometers. So what you can see is that there is a seasonal pattern in the Arctic sea ice extent. There's a winter maximum, which takes place in March. That's when the sea ice is at its greatest extent. And there's a minimum in sea ice area in September. So why I'm showing this is because of the impact that this increase in temperature is having. Now this plot shows the seasonal change in Arctic sea ice extent for every year between 1979 and 2020, with the earlier years in that series being in dark blue. And then we go through the colors of the rainbow, with the most recent years being shown in red. So you can see that every year has the same seasonal pattern, but over time there is a decrease. At any one point in the year, there is a decrease in Arctic sea ice extent. The minimum extent was observed in 2012, but 2020 wasn't far behind. And so why I'm showing this is to show you that over the last 40 years, the summertime sea ice extent has decreased by around 40%. And if this trend continues, it's predicted that by the end of this century, the Arctic Ocean will effectively be ice-free during the summer months. So that's one result of the warming temperatures in the Arctic, but there are many others as well. These are 3 news headlines that I pulled off the internet from the last year. The first one is about melting of the Greenland ice sheet. So that's the ice cap that is on land rather than sea ice. So that contributes to global sea level rise. The second one is about forest fires in Siberia, which had their most extensive year yet during 2020. And of course, this releases carbon dioxide into the atmosphere. And then the third one is about mysterious craters that have been appearing in Siberia and that could be linked to melting permafrost. So I included this one to bring up the issue of permafrost. As the temperature in the Arctic warms, permafrost begins to thaw, and that has it can have multiple consequences, including subsidence of the land, which can have which can cause major problems for infrastructure in Arctic communities. So why is the Arctic warming to such a great extent relative to the rest of the planet? Part of that is down to the change in albedo, which is the relative amount of the sun's energy that is reflected. So if you have an ocean that is covered in ice with a layer of fresh snow on the top, that will reflect around 90% of the sun's energy, and only 10% is absorbed. If you have ice with no snow, it still reflects around 50% of the sun's energy. But if you have open ocean, then only around 6% of the sun's energy is reflected, and the remaining 94% is absorbed. So what this means is that as the Arctic warms, we get a decrease in sea ice coverage, which means that there's more ocean to absorb solar energy. And as it heats, as the ocean warms up, that means that sea ice is less likely to reform. And so we get a sort of positive feedback effect. However, that's not the only thing that's happening. This is a schematic that I took from the MOSAIC website, and I just put it in to illustrate that the Arctic is a very complex system. There's a lot of interacting processes taking place. Some of these will result in other positive feedbacks, and some sort of offset each other. So for example, as the ocean warms, that is likely to affect circulation patterns. That can affect the supply of nutrients and the growth of plankton in the upper ocean. And that in turn can influence the exchange between the ocean and the atmosphere of certain chemicals. Those chemicals in turn, some of them play a role in formation of clouds, and that again affects the albedo of the planet. And so, like I say, this is just an example of some of the processes that take place in the Arctic. And then this final image from this section is a figure that I took from the latest report from the Intergovernmental Panel on Climate Change. And it shows the predicted increase in temperature by the end of this century as a function of latitude. So on the horizontal axis here, we go from the South Pole on the left to the North Pole on the right. You don't need to worry too much about the actual amount of temperature change here. What I want you to notice is that the blue band here represents the uncertainty in those predictions. And for the Arctic, there's a lot more uncertainty in future changes than for the rest of the globe. The reason for that is that many of the climate-related processes that take place in the Arctic are poorly represented in the climate models that are used to make these predictions. And the reason for that is a lack of data. And the reason that we have a relative lack of data for the Arctic is because it's very difficult to make scientific observations in the central Arctic, particularly during the winter months, because it's a hostile environment and because it's difficult to get there. So that's sort of summary of why we're interested in studying the Arctic. So now I'm going to talk about how MOSAIC will address those questions. A key aspect of the MOSAIC project is the idea of taking a research ship, the German icebreaker Polarstern, and freezing it into the sea ice in the summer months and letting it drift with the ice for a full year. The idea is to use the ship as a base, and because it's drifting with the ice, we can, in theory, study the same area of ice throughout a full seasonal cycle. And getting that seasonal cycle in data is very useful. I say that it's going to drift with the ice. The reason for that is the transpolar drift, which is an ocean current that flows across the Arctic Ocean from the Siberian side over towards Greenland and Svalbard. So this figure was taken from a planning document, and it just shows a prediction of how the Polarstern may drift in the ice over a calendar year. This is just a prediction. Obviously, there could be variations on this. And there is historical context for this idea as well. So the transpolar drift current has been known since the late 19th century. And when it, as evidence for this current began to mount, a Norwegian scientist and explorer, Fridtjof Nansen, came up with an idea to use the drift current to get close to the North Pole. His idea was to have a ship, the Fram, specially designed so that it could handle being frozen in the ice. In the summer of 1893, he sailed the Fram along the Siberian coast and took it into the Arctic sea ice in September. He let the ship freeze into the ice, and his idea was to let it drift and use it as a base for scientific observations and hopefully get close to the North Pole. He did not manage to make it to the North Pole, although the ship did get him closer than anyone else had done at that point. But his prediction that the ship would drift across the Arctic Ocean was correct. And 3 years later, the Fram emerged from the sea ice intact, close to Svalbard. So going back to MOSAIC, another aspect of the science plan, because we were going to be looking at the same piece of ice for a full year, the idea was to set up semi-permanent installations on the ice floe and use those as areas dedicated to specific aspects of the science. There was also a plan to build a runway on the ice, just by flattening the ice and making it suitable for aircraft to land, so that we could use scientific aircraft to support our science, and also to use it for personnel exchange if necessary. And not shown on this schematic, the plan was also to have a wider range of autonomous sensors in a distributed network, which would give us a wider area of coverage for certain measurements. The expedition timeline was for the Polarstern to depart from Tromsø in September 2019. It would, as with the Fram, it would travel along north of Siberia and enter the Siberian side of the sea ice, and then drift for a full year. But unlike the Fram, it wasn't expected that the scientists would stay on board for the full drift. Instead, the project was split up into 6 different legs. So although the ship would stay in the ice for the full time, the personnel would be exchanged throughout the year-long project. At the start of the setup, another icebreaker, the academic Fedorov, would travel up with the Polarstern to help with the initial setup. And then throughout the year, some other icebreakers from different countries would take part in the personnel exchange, traveling to and from the Polarstern from Tromsø with new scientists and crew for the Polarstern. The exception to this idea was between legs 3 and 4. At this point, this is close to the seasonal maximum in sea ice concentrations, but it was also expected that by this point, the ship would have drifted close enough to Svalbard that aircraft could be used to transfer personnel to and from the ship. In terms of the science taking place during MOSAIC, the aim was to be as comprehensive as possible, so we could sort of really look at these the interactions between different aspects of the Arctic system, and to simplify the logistics. The different projects were split up into teams depending on their main focus. So we had Team Ice, whose focus was on aspects of the cryosphere, ice, snow, and melt ponds. Team Ocean were focused on studying the water column, including the influence of currents and eddies on temperature and nutrient distribution. Team Ecosystem studied changes in algae concentrations and taxonomy, and also looked at zooplankton types and different fish species. Their main focus was on the energy and mass flow in the Arctic ecosystem. Team Atmosphere were focused on the vertical profile of the atmosphere. They looked at the radiative balance, they looked at aerosol concentrations and their sources, and concentrations of gases such as ozone. And then Team Biogeoscience studied the cycling of elements essential to life, such as carbon, nitrogen, and sulfur, and also used naturally occurring radioactive isotopes to trace exchange between the atmosphere, the ice, and the ocean. So that brings me to my own involvement. I was part of a project looking at the atmospheric supply of micronutrient and pollutant trace elements to the Arctic Ocean and sea ice. This was a project that was developed by Dr. Cliff Buck here at Skidaway, who I work for, along with colleagues from Florida State University and Florida International University, with funding from the National Science Foundation. So I mentioned trace elements. We are chemical oceanographers, and so when we say trace elements, we're talking about elements that are present in the ocean in extremely low concentrations, so parts per billion or even parts per trillion. By micronutrients, we're talking about elements that, even though they are present in low concentrations, they are essential to life and are required in small quantities by phytoplankton to grow. So this includes, for example, iron, zinc, and cobalt. And then pollutants are trace elements that have adverse effects on the environment, for example, lead. So we're interested in the atmospheric supply of these elements to the ocean. So by that, I'm talking about, first of all, transport of material from the land. So for example, in dry climates that are quite dusty, some of that dust can get blown up and carried up into the atmosphere, and it gets carried out to sea. Also, ash produced by forest fires and industrial emissions can carry pollutants. So these tiny particles, which we call aerosols, are carried out across the ocean, and eventually they get deposited into the ocean. They either settle from their own under their own gravitational mass, or they are scavenged out by rainwater. And the result is that these elements are introduced to the surface ocean. So it's quite easy for us to measure the concentrations of these trace elements in aerosol samples. We simply filter the air. I mean, we pull large volumes of air through filters, and then we analyze the filters to determine the concentrations of these elements. But that does not tell us about the rate of supply. So to do that, we make measurements of another element, in this case, a naturally occurring radioactive isotope, beryllium-7. So beryllium-7 is produced in the atmosphere, and it very quickly becomes associated with aerosol particles, and then it undergoes the same deposition processes. So it's introduced to the surface ocean in exactly the same way as the elements that we are interested in. Unlike those elements, this is the only way that beryllium-7 gets into the ocean. And the only way that it is really removed, usually, is by radioactive decay, which happens at a known rate. So if we are able to measure the total amount of beryllium-7 in the surface ocean, in theory, we can calculate the rate at which it is supplied to the ocean. And if we then have the ratio of beryllium-7 to the other elements that we're interested in on aerosol samples, we can infer the rate that they are deposited to the surface ocean. Of course, in the Arctic, it's a little bit more complicated because for much of the year, that deposition takes place onto the snow or onto the sea ice. And then those elements are released to the ocean during the summertime melt period. So for this project, what we intended to do was measure the inventory of beryllium in the snow and the sea ice and the surface ocean. And then, and then we would measure, we also plan to measure the ratio of beryllium-7 to the other trace elements in aerosol samples to calculate their rate of atmospheric deposition. Okay, so that's the end of the science, pretty much. For the rest of my talk, I'm going to talk about my own experience being involved in this project. The first thing to mention is that going to the Arctic requires a lot more preparation than most of the work that I've been involved in. So for this project, I had to go and undergo some firefighting training. I had to do sea survival training, both locally. This is me in a survival suit. And then this is me in Tromsø Harbor practicing. This is meant to replicate being able to pull yourself out of the sea ice, out of the ocean if you fall through the sea ice. And I had to have polar bear safety and firearms training. I'll talk more about that later on. In addition, I had basic first aid training, helicopter safety training, and I had to have a full medical evaluation before traveling to the Arctic. So I was part of leg 3, which meant that I traveled to Tromsø in northern Norway in late January 2020. And I met up with 55 other science personnel to travel north on the Kapitan Dranitsin, a Russian icebreaker. We got a nice display of the Aurora Borealis before leaving. We departed from Tromsø on the 4th of February. It only took us a day and a half to reach the ice edge in the Barents Sea. And the same day, we saw the sun for the last time for a few weeks. Because of the latitude and the time of year, we had 24-hour darkness for our journey northwards. So this is a photo that I took from the ship's bridge, looking down onto the ice in front of us. You can see the ship's spotlight lighting up the ice ahead of us. And this orange light on the horizon is the moon. I've put in a couple of videos that I hope play to give you an idea of our progress. So this first one I took from the back deck of the Dranitsin. You can see there's a bit of twilight on the horizon. The rest of this light comes from the ship, and you can see we're moving forward at basically a walking pace, which kind of sums up the forward progress for much of the trip. This next one is a speeded up time lapse from the ship's bridge, and I put this in to show that the progress involved a lot of forward and back and forward and back. And that's because icebreakers generally work by using their momentum and their power and their weight to break the ice. And sometimes this involves multiple attempts to break the ice, and sometimes you have to turn slightly to find a better way through as well. So the figure on the right here shows our progress between the 5th of February and the 20th of February. Hopefully you can make out that there are different colors. Each different color represents a different day. And then the white rectangles each have a different date in them. And at the top you can see the drift of the Polarstern over the same time in red. And I put this up to show that, the first few days in the ice, we made decent progress. But then very quickly, by the 9th of February, our progress slowed down considerably, and we were just making a few kilometers each day. And this is partly because, it was basically the middle of winter. And so this is when there's most sea ice, and so there's a lot more pressure on the ice, and it's just more difficult to get further north. However, we did eventually make it on the 28th of February. We rendezvoused with the Polarstern at 88.3 degrees north. So that's about 100 miles south of the North Pole. And in doing so, Kapitan Dranitsin set a record for the furthest north a ship has managed to get under its own power at that time of year. So this middle photograph shows the Polarstern in the foreground and Kapitan Dranitsin in the background. And we had several days of commuting between the two ships so that there could be a transfer of knowledge between the Leg 2 personnel and ourselves before they departed on Dranitsin on the 7th of March. Around about this time, we had the lowest temperatures that were experienced during the entire MOSAIC project. So on the 4th of March, we had a low of minus 44 Fahrenheit. But the temperatures were low in this whole period. And the lowest wind chill that we had was on the 10th of March. And that was minus 78 degrees Fahrenheit. A few days after that, though, we had our first sunrise in 5 weeks, which was a welcome return. And for the next few days after that, we had increasing amounts of daylight up until the 24th of March, At that point, we had 24-hour daylight, and we had 24-hour daylight for the rest of our time at the MOSAIC floe. So now I should talk about COVID-19. So when we were leaving Tromsø, COVID-19 was already in the news. At the time, it was mostly restricted to an epidemic in China. But obviously, it was in the news as we traveled north. We didn't have internet access on the ship, but we did have a daily news digest, and we had email access. So we were getting updates from family and friends. And obviously, COVID-19 was the dominant thing in the news at the time. And there was a lot of concern on board about the development of the pandemic during this time, concern for family and friends back home, and also concern about what it would mean for the project going forwards. On the 10th of March, so this is just less than 2 weeks after we arrived at the floe, we were informed that the springtime science flight campaign, which was supposed to support our science, had been postponed by a week due to quarantine requirements. And then a few days later, that was actually cancelled. This coincided with March the 13th. The US brought in travel restrictions from Europe and elsewhere. And on the 17th and 18th of March, the EU and Norway also introduced travel restrictions. So if you remember, our transfer at the end of leg 3 was supposed to take place by aircraft to and from Svalbard. Obviously, with those restrictions in place, this was no longer an option. So even from our early days at the MOSAIC floe, there was a lot of uncertainty about our return date. And there was also a lot of uncertainty about whether the MOSAIC fieldwork could be completed during the COVID-19 pandemic. And on top of this, everyone was very concerned about their family and friends back home. So during this time, we were getting on with our work, but the project management team was trying to find an alternative way to get us back home and to be able to carry on the project. As part of this process, we were asked our own thoughts about when we were comfortable leaving the ship and the maximum that we would be okay with staying on the ship, with the caveat that it may not be possible to get us off the ship by that time. And we were also invited to give our comments. So you can see here, there's quite a range in the dates when people were comfortable leaving the ship. And some people thought that the project we should consider terminating the project because of the developments elsewhere. Some people had serious concerns about getting back for visas or for upcoming surgery. So I put this up just to show that there's a lot of emotion going on the ship during this time. By mid-April, a plan had come together to get us off the ship, and that involved 2 German research vessels traveling to Svalbard to exchange the personnel. This would involve any leg 4 people that were able to travel to quarantine in Germany before leaving. At the same time, the Polarstern would have to leave the ice floe and travel south to Svalbard to carry out this personnel exchange. The Polarstern would then return to the floe with leg 4 people, while we from leg 3 would make our way to Germany on the other 2 ships. And overall, the plan was tweaked so that while it would still last for a full year, that would take place over 5 legs instead of 6. At the same time, it was acknowledged that there were people that really needed to leave the ship sooner than this. This timeline meant that we would not reach Germany until early to mid-June. And so a separate plan was organized alongside this to airlift around half a dozen people from the ship in mid-April to get them back home. And again, this had to be very carefully planned to avoid the potential for introducing COVID-19 to the MOSAIC ice floe. So during this time, we were getting on with our work. And then in the third week in April, we had to say goodbye to some of our colleagues. And then we remained on the ice floe, doing our work until mid-May. So I now want to take you for a tour around the floe to give you an idea of some of the work we were doing. The ship was the center of everything, and we had several installations around the floe: Met City, ROV City, Balloon Town, and Ocean City. You can probably, hopefully, make out the sort of orange ropes going out to the cities here. These are power cables. The idea was to, as much as possible, power these installations from the ship's power. So we had power cables snaking across the ice floe. You can see green and red flags here, which were used to mark out designated paths to certain parts of the ice floe, or to to make sure that places where people shouldn't be walking were well marked. And we even had signposts on the ice floe to help us navigate our way around. So Met City was an important hub for the team atmosphere people. It had a series of instruments and sensors for measuring meteorological data, atmospheric properties, and gas concentrations. Balloon Town was also used primarily by team atmosphere. The larger of the orange tents housed Miss Piggy, which was a tethered balloon which could be sent up to 1,500 meters. And it was possible to attach sensors for measuring temperature, pressure, turbulence, and ozone, amongst other things, to the wire to get a profile of those parameters as the balloon went up. Ocean City was basically a tent used to shelter a maintained hole in the sea ice. Through this hole, we would deploy a CTD rosette. This is used for sampling seawater, and it also contains sensors which measure things such as the temperature and salinity of the water. And it was also used for deploying plankton nets. These are some of the plankton that were recovered at Ocean City. It's an amphipod, and then these copepods, which are seen here through a microscope. ROV City was much the same setup in that it was a maintained hole in the ice that was sheltered by a tent. And this one was used to house a remotely operated vehicle, which could be sent underneath the ice floe to study the structure of the ice below and to measure the solar radiation, the intensity of solar radiation beneath the ice. And then on the ship as well, there was a lot going on. So the Polarstern is a designated research vessel, so it has a lot of lab space. But on this occasion, every square inch of the ship was put to use, as well as the labs, the shipping containers on the deck, some of which were used for storage, but others were converted to be used for laboratories. And then the ship had its own CTD, which is being deployed here by the crane through another maintained ice hole. So in this photo, the CTD is covered by a blanket, which is there to protect the sensors from the cold conditions. And as well as the more permanent installations around the floe, there was a lot of other science going on. These are two members of Team Ice making measurements of the physical properties of snow. There's a couple of members of Team Eco recovering a net that had been deployed under the ice. And these guys are measuring temperature along an ice core that's just been collected. Much of the ice floe, much of the work done on the ice floe was done within walking distance of the ship. But sometimes we had to go further afield, or we had a lot of equipment to carry. And so we had snowmobiles, and we had different sleds that could be used. And the Polarstern also has its own helicopter. And I'm going to play a video here. There's no sound. This is taken from my one and only trip on the helicopter as we're coming back to the ship. And I mainly put this in just to give you a bird's eye view of the ice flow. So you can see that the ice flow isn't flat. There's a lot of structure there. There are ridges. And as we go further around, you'll see some cracks with open water visible. I'm going to try and point out some places. This is ROV City here, where the cursor is. And we'll go further around. And in a second, you'll see Balloon Town. There's Balloon Town, and there's Ocean City. Another tent that was temporarily set up. And then we come around, there's another large area of open water. And then this is Met City. At the time that I took this video, Met City had been temporarily separated from the main flow. Okay, this doesn't go on for much longer. I'm going to pause that and carry on. So my own work, as I mentioned, we were interested in the beryllium inventory. So that involved sampling snow and ice cores. I also collected seawater samples. This is in the ROV tent, and I have a pump set up here. This is pumping seawater from 50 meters through this blue hose, and then it's pumping it out through the red hose and through the black cylinder there. That cylinder contained fibers which strip the beryllium-7 out of the seawater. These are our aerosol samplers, which were installed above the ship's bridge. And these were just used for sucking air through filters to trap the aerosols. And then this is my lab space, and these buckets all contain snow and ice core samples that are melting so that they can be processed further. I mentioned earlier on that I had to do some firearms and polar bear safety training to take part in this. Working in the Arctic, it's always possible that you can encounter polar bears. And this was a big safety concern for the project. It was taken very seriously. So whenever people were working on the ice, there was a designated lookout on the ship's bridge and another on the stern, basically just looking for polar bears so that people on the ice could be alerted. We had a small team of specially trained personnel who acted as bear guards for scientists working out on the ice floe. But the scientists taking part were also encouraged to have training to provide additional bear guard coverage for their colleagues. So each bear guard was supplied with a rifle and flares whenever they went onto the ice. But the priority was to avoid any confrontations. And so our most important piece of equipment was a radio to maintain contact between everybody on the ice and those on the ship. As it turns out, we only saw 2 polar bears during leg 3. One of them, this is the one that was seen close to the ship one morning before anyone actually went onto the ice. So it had a nose around some of the equipment and then moved away from the camp. This is a photograph of its footprints that I took a few hours later when I was on the ice. The second polar bear that we saw was off in the distance as we were leaving the floe. But overall, there were more than 60 sightings over the course of the expedition. Polar bears aren't the only challenge. Working in the Arctic, obviously, you've got to make sure your equipment can withstand cold temperatures. But given the very low temperature conditions that we experienced, even with those steps taken, you can run into problems. So this is a photo of a colleague demonstrating how quickly a cup of water will freeze in those temperatures. Storms and windy days were also a challenge. Windy days would create blowing snow, which reduces the visibility. And so in those instances, it wasn't safe for us to work on the floe because we wouldn't be able to see any polar bears. The other issue with blowing snow is that once we did get back out onto the floe, we had to spend time digging out equipment as a result. Ice dynamics were another challenge. I was surprised by, I'm not a polar scientist by training, so I was surprised by how dynamic the ice flow was. These two photographs were taken from the ship about 5 hours apart. You can see in the first one, as this crack begins to open, people are beginning to move equipment away from it. This photograph shows one of the consequences of this. The power cables here are in the water, and MedCity is on the other side of the crack. So on this occasion, MedCity had to be unplugged from the ship's power, and it was a few days before it could be reconnected. But these cracks also supplied opportunities. We're looking at the whole Arctic process, and this is one of the processes that occurs. So this is a photo of a colleague collecting a sample from the water that has just been uncovered. Ice doesn't just move apart. Obviously, sometime it has to move back together, and that can create ridges, which again can cause problems with access. This is a photo of people heading out to MedCity again after a ridging event. And this is a photograph of a piece of equipment that basically got eaten up by a ridge and had to be dug out and repaired. And finally, leisure time. You know, we were at the floe for a long time. Polarstern is a good ship, and it's designed to give it leisure opportunities for people working away in remote areas for long periods. So it has a gym, a sauna, and even a small pool, which was used for water polo. The area next to the ship was an area that was set aside for equipment storage, but was also used for running and for soccer on occasion. And we had a couple of hikes away from the ship to sort of explore sea ice further away. The ship has its own bar, which opens 3 nights a week, but only if there is someone on the science party that will volunteer to both bartend and clean up at the end of the night. We had special social gatherings on Easter and May Day, and we had games nights and movie nights. So going back to the COVID-19 situation, although I mentioned there was anxiety on board about the situation, we also realized that we were quite lucky in a way, because we were in the ultimate bubble, and we were still able to, during our time at the floe, we were still able to socialize with people throughout our time there. So we eventually left the ice floe on the 16th of May, when the ship had drifted as far south as 83 north. So that's the total of our drift. We spent another 2.5 weeks making our way south through the ice to get to the ice edge. We arrived at Svalbard on the 4th of June, and then the transfer began between Polarstern and between the Sonne and the Maria S. Merian. Those are the other 2 German research vessels. So I took this photo from the Sonne. The ship in the middle here is the Polarstern. This is the Merian, and this is a small fuel tanker that was refueling Polarstern at the time. After that, though the Leg 3 personnel continued south, we got our first sunset in 79 days on the 12th of June, and we arrived in Germany on the 15th of June. Before I finish, I should briefly mention what happened for the rest of the project. So Polarstern returned to the MOSAIC floe. That floe gradually drifted closer to the sea edge and began to break apart in late July, so the equipment was recovered. The final personnel transfer took place, again with special precautions to avoid COVID-19 getting onto the getting hold on the ship. And then Polarstern sailed further north to establish a new floe for the remainder of the drift period. It ended its drift on the 20th of September and arrived back in its home port on the 12th of October. It's early days for the MOSAIC project. In a way, the ship getting back was just the beginning. Some papers have been published already, but results are going to be coming out from MOSAIC for many years to come. I expect this project to have a big impact on Arctic science. So I know I've talked for a long time. I'm going to finish up by acknowledging the funding that we received from the National Science Foundation for our project. I tried to tell this story using my own photographs, but a lot of the time I found that other people's photographs did a better job of that. If you've been interested by what I've had to say this evening, I highly recommend that you check out the MOSAIC project website, and also this website, which has an archive of daily status updates from the project. And with that, I will open to any questions and answers.
Thanks, Chris. We've received a few questions in the YouTube chat. And I'm going to send you a link that you might put up on the slide there. The YouTube chat won't allow us to put it into the chat. And so while we read these first few questions, if you can put that on your slide, then folks can type it in. So we had a couple questions on there, not to make you do two things at once. Natalie was asking if there was when you showed the polar bear prints, it looked like there was a handheld radio there, and we were curious if that was was that for scale to show how large the prints were?
Hang on, I'm struggling here.
That's okay.
Yes, I put that radio there. That was my radio. I put it there. I put it there as a scale guide.
Oh, that's great. Yeah, I see a couple questions are popping in too.
All right.
There was a question by Aaron Tatum, which, basically, what happens when the work areas are cut off by main flows from water? So, like, if it's cut off by water, I imagine you have to find some other way around. Was the flow continuous enough that folks could make their way back to a ship through different routes? Yes,
generally, people took the long way around, which it sometimes took quite a detour, and so people were watching for cracks opening up from the bridge, and so if we saw that a crack was opening up, the people working on the other side would be told, and they were told basically finish what you're doing and try and make your way back, so that they would have the opportunity to get back before it potentially opened too wide. And then getting back to, getting out to do their work. Sometimes it was a case of sort of going out and finding a route, and sometimes it was just a case of waiting.
Yeah. Was there significant warning most of the time for the cracks opening up?
Yeah, we had plenty of eyes on the ice. There were people. There was always somebody on the bridge, as well as the polar bear watch. There would be someone else keeping an eye open to look for cracks. And generally, the time scale for these was such that there would be time to warn people and let them know.
Oh, that's great.
At least during leg 3.
By the time you were there, yes.
Yeah, so I mean, during leg 2, you had the added element of it was dark for pretty much the whole time. So I'm not sure how much of an issue that would have caused. And then obviously in legs 4 and 5 as well, that was much later in the season, so you would expect more open water. Yeah,
exactly. Clark was curious if folks took bottom samples, like of the ocean sediments through the sea ice at any point, or was it mostly focused on the ice and water properties?
Mostly the water column. I think there were sediment samples taken, but I don't know who did that. And I don't know how frequently that happened either.
Oh, that's great. Yeah, someone has the dirt somewhere, right?
I would think so, yeah.
I was curious myself about on the icebreakers. So I imagine all that back and forth motion when you were breaking the ice is really noisy. Were the living conditions okay? Like, are you isolated enough from the noise that it's not so bad?
Sorry, just give me a second.
Sure.
I'm just trying to get this link up.
And while you're doing that, a lot of folks are saying it was very informative, and thank you very much. So those non-question statements are coming in as well.
Can you see my screen now?
Nope, you have to reshare again.
Okay, sorry. Share screen.
I put it in there into the chat with a little bit of spaces. Yeah, there's the link there. So if folks want to submit that form, I can read a few questions from that.
Can you see that now?
Yes.
Okay, great. Can you repeat the question?
Oh yeah. So I was curious how noisy the breaking the ice was. Was it comfortable enough while the ship was doing all that back and forth motion and noise?
You got used to it.
Yeah.
It was quite noisy on Captain Dranitsin, particularly. On Polarstern, on the way back, I think I was on a higher deck, and so it was less noticeable.
Mm-hmm.
What was pretty crazy for me was while we were at the floe, the lab that I was working in on Polarstern was below the water level.
Oh wow!
And so as ice moved against the ship, I could hear it sort of scraping against the hull.
Oh wow!
Yeah.
The only thing worse than that scraping is when it stops suddenly and you wonder why the ship has stopped, right?
Yeah.
Charlie was asking, you mentioned that one goal was to power the camps via the ship. Were there like solar panels used as well to complement that for the parts of the cruise when there was sunlight available? Or is it just not possible with the Arctic conditions?
I'm not aware of there being any solar panels. And I'm not sure why not, if that was the case. From my own experience, the periods when places were cut off from the ship's power, we generally used generators. And so the photo that I showed of people clambering over the ridge, one of those people was carrying a fuel can. That was to refuel a generator out at Met City.
That sounds great. Dragging a bunch of gasoline across diesel across the ice, right?
Yeah.
You mentioned near the end there that that there are already some papers published. I was curious, like what were the big scientific results while you were there, if there were any? Like you said, a lot of the data doesn't come out till later, but there must have been some surprises while you were there.
You know, I haven't really looked at the data that's come out yet. I think there's been a paper which sort of is about the origin of the MOSAIC ice floe. There was analysis done on any sediments that were in the floe, and it was determined that it was formed off the coast of Siberia. So I know there's been a paper about that. There's been at least 3 or 4 papers about aerosol studies in terms of signals from forest fires at high altitude. And this, I think this all comes from the LiDAR work that was done. So LiDAR it sort of sends a pulse of light up through the atmosphere to determine aerosol concentrations high in the atmosphere, and they can even tell what types of aerosols are up there.
Oh, interesting. Yeah, there's a question from David Harper asking about how often the Northern Lights were visible.
Not as often as I'd hoped. So we had one really good show when we were on the ship before we left Tromsø, and a couple of weaker weaker nights at around the same time. Once we got further north, well, we had a few overcast days, and then didn't see them very often. Apparently, Tromsø is pretty much the best place in the world to see the northern lights because of the latitude. There's a maximum intensity of them. I think it's 78 degrees north where Tromsø is. And once you go further north, although you can still see them occasionally, they're not as intense as you see them in Tromsø or Fairbanks as well.
Yeah, and 2019 was the minimum in the solar cycle as well, right? The like 11-year solar cycle. So you're sort of at the bottom of activity in general, too.
Right.
Oh, that's great.
Yeah.
Let's see. Oh, I have a question on the Google form. It says, you mentioned that it took the Fram 3 years to drift across the Arctic in the 1890s, but the Polarstern did it in under a year. Has the transpolar drift current sped up, or is it just down to less ice now?
Good question. I can't answer that definitively. I think part of it is because there is less ice. We were further north when we started. I have seen one study that suggests the transpolar drift is speeding up, but I don't know, how definitive that study is. And I think some of it is luck as well. From my own experience, the weather systems that came through had a big effect on our drift rate. So if a storm comes in at the right angle, it's going to make you drift faster. Or if it comes in from the other direction, it's going to hold up your drift rate. I know that for the Fram, their first few months they sort of meandered quite a lot. I think that that could also be related to eddies, which if they were unlucky enough to start their drift in an area with a lot of eddies moving through the water, then you sort of find yourself drifting backwards and forwards quite a lot.
Well, you could see in some of those pictures, the ice was fairly thick, right? At least a meter thick in most places. I'm guessing the thickness of the ice has changed since the 1890s as well because of the extent of multi-year ice, right?
Right. Yes. So I did have an image in my talk originally, which I had to cut. So it's like back at the start, I had another image that showed the change in the age of the ice over the last 30 or 40 years. So because it's melting a lot more now, it's moving to a much more seasonal ice. So there's more 1-year-old and 2-year-old ice, whereas 30 years ago, around half of it was 3 years old or more. And so in that case, you have thicker ice. Whereas these days, it tends to be thinner. Yeah, much of the ice flow when I was there, much of the ice was the first year ice was about 1.5 meters thick, and then there were areas where the ice is older, and it can be 2 meters thick or more. And then there are also areas where it's ridged together, or ice flows have sort of slid on top of each other like that, and then it can be several feet thick.
Oh, interesting. Let's see. Refresh my form here and see if any other questions have come in. I don't see any there. A couple more thank yous. Such a fascinating experience you've had. Your presentation was excellent.
Thank you.
Oh, and then Aaron had a follow-up question, which I didn't see. Yeah, would it have been possible for a floe to cut off access fast enough, to sort of trap a team, or did that seem unreasonable based on how fast things were going?
You mean for a crack to
Yeah, for a
Yeah.
crack or like a ridging event.
It was plausible, yeah. But I mean, we did have the helicopter as well,
Oh, that's true. Yeah.
and on occasions the helicopter was used around the floe to move heavy equipment, and it could be used to go and pick up people as well, assuming that conditions were suitable for the helicopter to fly.
Yeah.
And actually, adding to that response, as people went further away from the floe, there are requirements for them to take survival equipment. So, the further away you go from the ship, the more danger you have of being cut off and being unable to get back in a timely fashion. So there were strict protocols for if you go a certain distance, you must take this equipment. And that would include like a survival bag, a tent, some food.
Oh, that's great.
Yeah.
Cool. Well, I see we're quite a bit past 8 o'clock, so we should probably end the Q&A session here. I think Mike wanted to jump in.
Great, thanks. Yes, thank you very much. And I want to talk about our next Evening Skidaway program in 3 weeks. And our speaker is none other than Dan Onimus, who's been running the Q&A here. So Dr. Onimus, let me kick it right back to you and give us a little heads up on what you're going to be talking about.
Yeah, folks can see the title there. So I had a little blurb I prepared. Let me pull it window up. Yeah, so we, as Chris mentioned in his talk, we spent a lot of time thinking about climate change and constraining the uncertainties. But we haven't spent a lot of time talking about mitigation strategies and intervention strategies. So in this talk, we'll take a look at some of the simple potential solutions to mitigating climate, like carbon markets, and some other sort of more complex or even outlandish sounding ones like albedo modification or adding rocks to the oceans. And so, yeah, we'll take a look at these different strategies in the next talk coming up in a couple weeks.
Great, and I'd like to remind those who are still with us that you'll find us in the same place, the Skidaway Institute YouTube channel. The link for the individual talk that you find will change from talk to talk, but if you just go to the channel and you'll be able to see the feed. And here's a look at the rest of the year. We'll have monthly programs through the month of November. And I want to thank everyone for joining us here this evening. And we'll see you on April 13th. Bye all.